Unit 7, page 210 to 211, Integration of Composite Functions. For each of the functions given below, find both f prime of x and the definite integral of f prime of x dx. So if we remember from when we were doing derivatives, composite functions require us to use chain rule when finding the derivative. So we want to apply that chain rule to the f prime of x. So just really quickly, I just want you to go through and determine the derivative for all 4 of these functions. You may need to rewrite some of them in order to do so, but you do have the skills to find the derivative of all 4 of these functions using chain rule. And if you forgot what chain rule is, I'll just put it down at the bottom. So d dx of f of x of g of x is equal to f prime of g of x times g prime of x, right? The derivative of the mama with the baby times the derivative of the baby. So once you've found the derivative for all 4 of those functions, we're actually going to find the antiderivative of all 4 of those derivatives. So for the first function, you should have gotten 3 cosine 3x, and we're going to find the antiderivative of that. So if you notice, when finding the derivative of a composite function, we find that you take the derivative of the inner function and multiply it by the derivative of the outer function. So when taking the antiderivative of that derivative of the inner function is very helpful to notice, because then all we have to do is just take the antiderivative of the outer function with the baby. So when you notice, so let's do another function. So we have antiderivative of negative sine x times e to cosine x dx. Negative sine x is the derivative of our inner function cosine x. So when taking the antiderivative, we just have to take the antiderivative of our outer function, which is e to the x. Antiderivative of e to the x is just e to the x. And we're going to keep our inner function. We'll do a lot more practice of this as we go along. So the antiderivative of 2x over x squared plus 3 dx. So here, our inner function is x squared plus 3. The derivative of that is 2x. So we're going to take the antiderivative of 1 over x squared plus 3, which is ln absolute value of x squared plus 3 plus c. And when you take the antiderivative of a function and it's going to be ln, this is just rule of thumb. The antiderivative, when you get an ln function, you have to put the absolute value, because ln, you can only use the ln function if your input is positive. So just make sure you put that. It's not a complete game changer, but it is really helpful just in the future purposes. And then our last function, the derivative of that was x over square root of x squared plus 3 dx. Now, x squared plus 3 is our inner function. The derivative of that is x after we've done the square root business. So our final function is just going to be square root of x squared plus 3 plus 6. Okay, so what does that help us with, right? So if we are integrating a function and we notice that the function is in the order of chain rule, right? It has an outer function, an inner function, and is multiplied by the derivative of the inner function. Then our antiderivative will just be the antiderivative of the outer function with the inner function plus c. Okay, we consider that g prime of x, that gives us license. That's not how you spell license. That gives us license to integrate. Okay, this might be a little confusing right now, but we're going to do a few problems that hopefully will clear this up a bit for you. All right, so for example, for problem number 1 on 211, we have the function 3 cosine 3x dx. Now, if we look at this function closely, we have an outer function cosine, an inner function 3x, and it's being multiplied by 3. If we look at our inner function 3x, the derivative of that is 3. So because 3 is the derivative of 3x, this gives us the license to integrate. Okay, it gives us the license to just find the antiderivative and just make sure that keep the 3x within that antiderivative. So the antiderivative of cosine, we know, is sine. And in order to make sure that we have the license to integrate, we're going to keep 3x inside and plus c, because this is not a definite integral. Okay, a few more problems together. So here, we're first going to rewrite this problem. So we have 2x times x squared plus 5 to the 1/3 dx. Okay, so here we are again. The inner function is x squared plus 5. The derivative of that is 2x. This gives us the license to integrate, because the derivative of 2x plus 5 is 2x. So this gives us the license to integrate our outer function. Okay, so what that means is we want to find the antiderivative of something to the 1/3. Right? This is in polynomial form, so we know that we're going to add 1 to my exponent, so I have 4/3, and we're going to divide our previous constant by our new exponent. So the previous constant to this function was 1. We're going to divide that by 4/3. And then we just want to make sure that we keep our inner function, which was x squared plus 5. So this becomes 3/4 x squared plus 5 to the 4/3 plus c. Okay. So for the next problem, we have 2 sine 2x plus 3 dx. 2x plus 3 is our inner function. The derivative of 2x plus 3 is 2, which we see here. So this gives us an okay, a license to integrate. So we're just going to integrate sine. And the antiderivative of sine is negative cosine. And we want to make sure that we keep our inner function, which is 2x plus 3, and then plus c. All right, so then for this last function, this function, if you look at the numerator, 2x plus 2 is the derivative of x squared plus 2x. So if we think about a function whose derivative is the derivative divided by the function, that brings us to ln. So we have ln of our bottom function, which is x squared plus 2x plus c. ln is the only function where the numerator is the derivative of the denominator. Okay. So now we're going to look at problems where the license to integrate is not obviously in the problem. Okay, so here we have the antiderivative of cosine 3x plus 2 dx. So our inner function is 3x plus 2. And the derivative of 3x plus 2 is 3. That is not explicitly in our function. So what we're going to do, because the derivative is just a constant 3, we can actually just multiply by 3. Okay, so we're going to have the antiderivative of 3. Sorry. Yeah. So we're going to have the antiderivative of 3 cosine 3x plus 2 dx. And now to keep this function level or equal to the function we were given, we want to also cancel out the derivative because it wasn't there, right? So since we put something in, we want to be able to cancel it out. We can't just rewrite equations by adding something to it without canceling that out. Okay, so now we have our inner function and our derivative. So this gives us now a license to integrate. So we're just going to integrate the cosine function. So we'll have sine 3x plus 2 plus c. And since we had to put in the derivative and take it out, we have to make sure that we keep this balanced, right? Because this gives us the license to integrate this piece, but it doesn't give us the license to do anything with the 1/3, so we have to keep that with us. Okay, so for our next problem, we want to rewrite this, so we have 3x square root of, times x squared plus 2 to the 1/2 dx. So here we are again where we have the inner function, which is x squared plus 2. The derivative of x squared plus 2 is 2x. We do not have a 2x here, so, but we do have an x. So a constant that we can multiply this by is 2. And in order to make sure we cancel that out, we have to also multiply by its reciprocal 1/2. So now we have 1/2, and since the derivative of x squared plus 2 is 2x, we want to make sure that the only thing in our integral is the derivative. So this 3 needs to come out. So 1/2 times 3, and then we have 2x, x squared plus 2 to the 1/2 dx. So now this gives us the license to integrate this integrand. And then out here, we have 3/2. So when we integrate this integrand, we're going to add 1 to the exponent, so that's 3/2. We're going to keep our inner function, which is x squared plus 2. And then we're going to divide our constant, which was 1 here, by our new exponent, which is 3/2. So we're going to have so this gives us x squared plus 2 to the 3/2 plus c. All right, we're going to have 2 more to do here. So for this problem, Our inner function is 3x. And the derivative of 3x is 3. So we want to make sure that we have that derivative. So if we rewrite this, we want 3 5e to the 3x. And to make sure that we cancel out that derivative that we just added in, we want to multiply by its reciprocal. Okay, so again, the only thing we want in our integrand is the function and its derivative. So we're going to take this 5 and bring it out. So we'll have 1/3 times 5 integral of 3e to the 3x dx. So now this 3x gives us license to integrate because 3x and its derivative are both there. So we have 5 over 3 e to the 3x plus c. So now this last problem, we're going to rewrite this. Gives us the integral 3x times 2x squared plus 3 to the negative 1/2 dx. The derivative of our inner function, so our inner function is 2x squared plus 3. The derivative of that is 4x. We do not currently have a 4x, but we do have a 3x. So we want to multiply this by 4. And to make sure that we can cancel out that derivative, we want to multiply by 1/4. So once again, we're in a situation where we only want the integrand to contain the inner function, the outer function, and the inner function's derivative. So this 3 needs to come out. We only have the license to integrate the inner function's derivative. So now we have 3/4. And to integrate this function, we're going to add 1 to the exponent. So we have 1/2. We're going to keep our inner function, which is 2x squared plus 3. And we're going to divide our constant by our new exponent. So 1 over 1/2, which will give me 2 over 1. Which is equal to 6 over 4 or 3 over 2. 2x squared, 3 to the 1/2 plus c. Okay. So this process is just integration of composite functions by pattern recognition. The next video actually has a specific step-by-step pattern that you can follow to integrate any composite function, even if you can see the derivative of the inner function.